Today I want to go over how to quickly and repeatably generate a 5-axis radial toolpath. In today's example, I have a flange here that I need to machine all the way around the outside of the part, 360 degrees. And I also need to get in between these gussets. So to do that, what I don't want to do is I don't want to generate several toolpaths to come in here and machine all this out. What I would like to do is have a ball mill come in and surface all of this. To do that, there are just a couple quick steps, and the first thing being is that we need to dictate what type of feature we're going to generate, what type of feature we want to run our toolpath to. And first things first, I would like to just only grab what I need to machine. Typically speaking, when I go in and I build the toolpath for the first time, I will leave out my check surfaces. So my FreeForm right now, it currently has the model as the check surface, and the part is what I want to machine. Again, going back to what I said earlier, what I would typically do first is leave the solid part out, the check surface out, because what I don't want to do is I don't want to get into machining, or I don't want to get into trying to generate the toolpath and figure out that I have broken toolpath, patchy toolpath. If you leave the solid out first, it may collide with the part itself, but at least you'll have toolpath to go back in and dictate the orientation or the linking strategy to get around it. But it's better to have toolpath first and then go back in and modify and manipulate it the way you want than it is to have nothing. So in this instance, I'm just going to go ahead and create my check surface because I've already gone through the hoops and bounds, which I'll walk through here in a little bit. Just trying to figure out what works and what doesn't work with this toolpath. I will say this is very straightforward and simple, and there are very minor changes that need to be made. So this is the FreeForm feature, and we will move on to the type of operation that I'm going to utilize. Next, we're going to move over here to our FreeForm tab and then go to Composite. Composite Cycle, it is one of my favorite cycles. It is really easy and difficult at the same time. It just depends on what you're trying to do and how you envision the type of toolpath that you're trying to construct. So in this instance, what I'm wanting to do is I just want to run the tool radially around the part. I want the part to spin. I want the tool to stay still. There are instances where I will want the tool to tilt, which I will go in and manipulate the orientation strategy. But for this one, in this instance, I'm not going to do that. This is just going to be an introductory level type video for our composite cycle. So we have our FreeForm feature and we have our composite cycle. So I'm going to open up this operation I have here. I'd already built, but I will walk through it step by step. So we're going to start off on the general tab. I just named it operation name radial 5-axis, 3/8 ball mill, finishing 4-flute ball mill. And the only thing I changed was my speeds and feeds. You have to have this for calculation purposes. Moving on to the toolpath, the next thing I would do, generally speaking, is go to your tolerance up here. This from the standard default on this one was 5/10. When I'm starting out trying to do any type of toolpath, typically I would set this to about 3 to 5 thousandths. And the reason for that is because of calculation time. So it's rare that you'll actually get the perfect toolpath exactly the way you want it the first time. The last thing you want to do is continuously go in and modify your toolpath. There are ways outside of this to go in and manipulate the toolpath outside, such as your properties tab down here. But sometimes it's easier just to see what your options are when going back into the operation itself. The edits that can be made to the properties tab down here can be done outside of the operation page. But then again, sometimes it's better just to see everything in whole. So in this case, I already had this dialed in, so I'm going to set this to 1 thou. And moving down here, the machining pattern, what I like to start out with here is the parametric pattern. And then if I want to, this is good for driving to specific surfaces only. I say only, but it's good for driving to specific parametric surfaces. So if I only wanted to do one of these up here, it would be great to just go ahead and select this surface here if I wanted to machine this. However, because I'm machining all the way around and I want it to follow a specific orientation, I want it to rotate in a specific direction, I want to have full control over that. outside of the surface parametric lines or parametric pattern or what have you itself. So what I'm going to do is I'm going to select parametric spiral. So before you get into this operation, and I kind of did things out of order in this manner, mainly because I needed to show you what I wanted to do, and the next would be how to do it. So the surface here, I constructed a cylinder. All I did was I came over here and I created geometry first. So the geometry was just a circle here at the beginning. And then once I have my circle, then I can go in and just extrude a surface. This is done through the modeling tab. It's not very difficult at all. So again, I created a circle here, and then through the modeling tab, I used extrude. So going through the steps of extrude, you can then create your surface. And then once you have your surface, this is what you can project from. So the reason why you would want to have a surface rather than just selecting this is because the circle here is all encompassing. It doesn't have any breaks. Its parametric lines are hypothetically perfect. You can see there are no breaks, there are no bends. All of our parametric lines on this surface are cylindrical. They are straight. They do not twist. They do not bend. They don't move. And in essence, it's absolutely perfect when it comes to a surface that you would want to machine. If I were to just utilize anything on the surface here, their parametric lines may bend around this corner. They may go front to back. At least in this manner, in this instance, we can dictate exactly what we want with our parametric lines just by extruding a surface. So going back in, you'll see that the surface is selected, but then we have to worry about a couple of other things. I say worry about it, we just had to pay attention to it. So when we click on our drive surface, what you need to pay attention to is our vector angles from the surface itself. The biggest two being is A, the direction of our red arrow, which would be our U, or the direction of our green arrow, which would be V. The machining direction down here in these options will be dictated by these arrows, which there are pictures, which is really nice. I like pictures. The next portion of this is our orientation vector here, which is always the white vector. And again, pictures are worth 1,000 words, so we'll go through the steps right here. So cutting direction. If I look at this, what I need to pay attention to is the direction of our cut versus the direction of our X or our red vector or Y vector for our green vector here. So paying attention to that, what I want to look at is I want my machining direction to be in the U direction. So that would be the next thing I would check, which this was my default was the U direction. So I do want to machine here. If I wanted to machine front and back, which to each their own, if you wanted to machine front to back, this is where you would set your direction to V. So V direction would cause our tool to go forwards and backwards, but it would still follow this radial path. The next portion of this is reverse cutting direction. I don't really want that. Reverse step over direction. I don't want that. So the reverse cutting direction would be I want the machine front to back, not back to front. If I wanted to go back to front, I would reverse cutting direction. And then your step over direction would be the exact opposite. So these can be used to counter one another per se, but this would depend on quite a few things. Climb versus conventional, and in this case, it's really not pertinent to go in and mess with any of these, but this is where you would want, if you wanted to start in one position and move back, start in the back position and move front, vice versa. This is where you would manipulate those, but this instance, it really doesn't matter. Reverse projection side. So the big thing to look at here is, again, our white vector right here. So ideally, if we wanted to project from here down to the part, we would want this white vector pointing out of our surface. Right now, we don't have that, so there is an option here to reverse projection side. So again, clicking on this, we have pictures. So right now, it's if yours looks like this, you don't want to project it. If yours looks like this, then you do want to project it. So that's why it says reverse projection side, yes, because our vector is pointing towards our machining surface. So this is what we want to select. The remainder of these I'm not going to manipulate. These are all system defaults here. The only thing I will do is change the incremental step over, which I just put this to 5%. This will lead you to probably a 64 finish, 62 finish, give or take. If you wanted a finer finish than this, you would drop it down to 3%, 2%, what have you. Again, to each their own, whatever you're trying to achieve. The next thing on here is if you want to scallop height, if you had some intricacies that you needed to get in between, if you had peaks, valleys, what have you, if you want to step down a wall, this is where it'd be better to use an optimized scallop height, but again, I'm not going to go through that on this one. Moving on to the orientation strategy. Again, going through here initially the first time, I would leave all of this empty. The only thing I have changed in this field itself is the angle limitation. So fixed with angle, z-axis 75 degrees. So some may ask, what does this mean? What does the z-axis mean? What does the UVW axis mean? So z-axis means XYZ. So everything is brought in on XYZ plane. Just think of XYZ as just your standard work plane. So in this case, I built my feature, my FreeForm feature, around the XYZ work plane. This may seem counterintuitive, so this may seem like it's going against the grain. When it comes to 5-axis, generally speaking, you do want to set your work plane accordingly to the type of work you're going to do. When it comes to radial, I will say this is when things get a little different. So I did XYZ, but that's because I want to spin around the z-axis. So setting this in XYZ, I have the ability to dictate my toolpath, especially the orientation angle. So orientation angle, you see up here, fixed angle 75 degrees. Why did I use 75 degrees and why did I use a z-axis? Z-axis is here. If I set it to z-axis 0, that means I would try to machine from this direction only. I don't want that. If I set it to 90 degrees, it's going to lock to 90 degrees. It'll still allow me to spin around the axis, our z-axis, but it's locking to 90 degrees, which machining with the center point of the tool is not the greatest idea, especially if you're trying to optimize your surface speed. So what I did is I set it to 75 degrees. This gives me a 15-degree angle kick off of 90, which allows me to utilize more of the radius of the ball off center, which will allow a better surface finish, more surface speed per cut, per tooth. It's better all around for surface finish and pretty much surface quality. That being said, I had it kicked to 75 degrees, z-axis. One might ask, why did I not use x-axis locked at 90 degrees? So if I locked it at 90 degrees, this does not give me any other direction of rotation, which means if I were to lock it at x-axis right here at 90 degrees, or I'm sorry, this would actually be at 0. If I did x-axis 90 degrees, it would be as if I was trying to machine through z. X-axis 0 orients it in this direction, but it will not rotate the part. Because if I lock it to if anything is locked to 0, so XYZ, if it's locked to 0, that means it's going to only look at this surface from that plane. It will not rotate. It will lock the tool in that axis, and it will not do any type of 5-axis movement. This can be beneficial for, let's just say, any other type of machining or surfacing you're trying to do, but this is not what I'm trying to do now. I'm trying to do radial surfacing. All right, so moving on. The only other thing that I changed was in my links, and that is because I don't like my tool coming out and then tilting back over 90 degrees and then tilting back and then driving in. This is where I usually set my rapid links to radial around axis only. So if I do radial around axis, z-axis, and radial offset factor, there's different options in here. Z-axis, again, being XYZ. I set it to z-axis. Offset factor, I try to set this as close as possible. You'll see a -2 in here. It didn't really take effect, so respectively, I'll just set it to 0, and then you can come up here and manipulate your clearance and full clearance. But again, radial around axis, even if I came in and system defaulted that one, it would stay at 1. So that being said, radial around axis, 1. This will get you 99% of the time where you want to be. Later on, I'll make another video about the entry exit feed links, because sometimes building these operations, you'll get error messages down here in your event window. And it'll say try changing entry, try changing exit. This has a lot to do with your entry and exit and your links. These do control quite a few things, which again, I'll go through at a later date. All right, so that being said, I'm going to hit OK. I don't think I changed anything in here worth mentioning. So right now you're going to have everything building over here in your program tab. So once that gets complete, we should see our 5-axis operation here. So again, it kept it projected from this surface to our machine surface. And going over here, I'm going to remove our surfaces and our geometry. And next, what I'm going to do is I'm going to go over to our simulation tab and hit single step. And I'm going to bring it over to the cut just so we can see that it tries to orient. It goes over. And first thing it does is it gets over here to our first point of contact. So at this point, I'm going to back up. I'm going to let it run its course. And right now it is kicked at a 15-degree angle, again, keeping it off the center. So it can do its machining, so it can actually maximize its surface speed. And what you'll see is it'll not only move radially, it'll spin up, but it'll also step over incrementally as well, which, because we set it to spiral, it's going to be a continuous move until it gets to broken toolpath. When I say broken toolpath, I don't mean the fact that it's inaccessible. Broken toolpath means that when it gets into the cut, it has to stop and change direction. So what you'll see right here is that it's machining a small portion, then it's moving to the next, machining a small portion, but then it'll eventually get to a point where it makes more sense to stay in the cut than it does to reposition. So this would be the first section that would be a cause for the tool to stay engaged, and its feed links wouldn't dictate a necessary movement to the next cutout. If you'd like to see more of these tutorials, you can subscribe to our YouTube channel to receive alerts when new content is posted. Or you can also find these videos and correlating blog posts on our website at pmtechnologies.com.